computer. So sorry about the chaos. So the second theoretical exercise was about a bit more synchronization, and yeah, let's go into details here. So the first question was about race conditions. So we had two parallel threads, T1 and T2, that share their data. So we have one address space, so it's threads, not processes here. And we have two initial values, 0 for all variables y and z, or z. I prefer the British English pronunciation of z, but yeah, just, yeah. Well, we use whatever you like, obviously, when you're talking about it, but just to reduce confusion here. So the first thread is declaring a local variable x, and it just adds our two variables x, y and z together. And the second one just sets these two variables y and z, the y to 1 and z to 2. And the first question was to give all possible final values for x and the corresponding number of execution of instructions in T1 and T2. So essentially, which the corresponding order of execution. My goodness, I should learn reading. Yes. So essentially, you should figure out like where could a context switch between threads happen, and how does this affect this shared values of y and z and our result. So the first example would be T1 starts, runs to the end, and afterwards T2 starts and runs to its end. So when this happens, then the initial values of 0 are in y and z, and obviously we calculate x equals 0 plus 0 and get the result 0. That's the most uninteresting point, I guess. So what else can happen? Let's say T2 starts first. Of course, only because we numbered them T1 and T2 doesn't mean that T1 has to start first. So let's say T2 starts first, and that's again a decision by the operating system scheduler if you have kernel level threads, for example. So T2 could run until the end of line 2. So it sets y to 1. Then we could switch over to T1. Then we could calculate x equals y is 1 plus z is still 0. So we have a result 1. Or we could have T2 run to the end. So it sets both y and z. And then we could have a result of x equals 1 plus 2 is 3. Is this all? And that's a big problem when doing these synchronization problems. Have I actually managed to catch all of them? So are there other possibilities giving additional values? So yes, there's additional information by Hova. Again, the compiler is allowed to reorder the assignments to y and z. Volatile would actually change this, and on Intel, the memory model is total right order. So yes, you don't think we could get x equals 2, but on ARM order, you would get it. So these are really details that are important, which are a bit advanced for this semester, I'm afraid. So this needs to be discussed, definitely. Yes, but there are maybe other possibilities giving additional values. Let's take a look. This depends on the storage order model, as Hova already mentioned, but also on code generated by the compiler. Because what happens with your task switches is that they do not occur between your lines of C code, because these lines of C code are nothing your processor sees, but they happen between separate machine instructions. So usually when you do an addition like this is done in separate parts. For example, if you do this line 3 and if you implement it in machine code, it first fetches, for example, the operand y in a CPU register R1, then it fetches the operand z as the next machine instruction into another register R2 here. Then it performs the addition of the register values on a RISC CPU, for example, stores this in yet another register R3, and finally it stores R3 in the memory location of X. So let's see what I wrote here. So the task switch to T2 occurs between machine instructions A and B. So between the fetch of the operand Y and the fetch of the operand z. What could happen then? So we execute x equals y. So we load y first, which is 0. Then we switch over, set y and z. We have already read y. So we read z in the next step, read z as 2. So we have our cached value of 0 in R1. We have our value of 2 in R2. And then we write back a 2. So this sum would actually be a valid result here. So essentially that can happen. So just looking at these problems from a C source code point of view doesn't give you all the details, and you have to know details of like, is this done in one instruction, this addition here? Usually not on modern RISC machines. And also more intricate details like the store order, for example, that can happen here. Okay. And this is, of course, because this addition is itself a critical section. So the question was, is it possible to use semaphores so that we can force the final value of x to 2? That was the first question. The second part of the question. There was a typo. If not, explain why not, except instead of no as I typed. So what we can do is we can, of course, protect the critical section with a semaphore here. But that would only guarantee that x can never have the value 2, right? So if we want the opposite, that x is 2, this would actually require that we change our source code by splitting this operation 4 into separate parts and then putting semaphores around it. But of course, that was not what it was intended because that would modify the original source code. So essentially forcing it from a C source code level is actually difficult. So more semaphores. So here we had 2 threads running in parallel as always, and they print separate characters here. And your task was to insert semaphores and wait signal calls into those threads so that you print the word Wordle. Yes, I'm playing it every day right now, and it's still fun. So what you have to do is essentially to guarantee an order of 2 processes. So what we want is, we want first the W to be printed, then we want to switch over to T2, that O and R are printed. Then we need to switch back to T1 to print the D, and finally switch back to T2 to print L and E. And we can do this like shown below. So first, we'll wait for S1. So we have to guarantee the starting order for threads here because we don't want T2 to start first because then we have an O at the beginning and not a W. So we wait for semaphore 1 first, then we print the W. Then we signal semaphore 2, which is in thread 2. So thread 2 was waiting for semaphore 2. This can then print OR. In the first thread, we then wait for the signal on the other way around. So signaling back from T2 that we can continue, then we can print the D. And then finally, we signal for the second wait in T2, so it can print L and E. So what we have to do now is we have to ensure that T1 starts first and T2 starts second. And we do this by initializing the semaphores to appropriate values. So if we would initialize both semaphores to 0, then we would never print anything because then both T1 and T2 would be waiting infinitely on a semaphore value to reach 1, which it doesn't do because nobody's executing signal on these signals, on these semaphores. So we need to ensure that T1 gets into this printf instruction here at line 3 first. So we wait for S1, and in order to enable it to get into here, we initialize the value of S1 to 1. And we don't want T2s to start right away. So we initialize the value of S2 to 0. And this is only set to as to 1 in line 4 of T1 after we printed the W. And this is the whole trick here. So there's a question, is it valid to initialize both to 0? and then not start T1 with S1.wait. Yes, that would be an alternative. Exactly. We could also do this. So that's just one of the solutions. But of course, you have to synchronize your code and your initial values here in order to make this work. Yes, so if we omit the first S1.wait, so line 2 in T1, then T1 would start right away, but then we'd have to set S1 to 0, because otherwise we would just fall through line 5. Right, more semaphores. Yeah, I think you're getting sick of semaphores. So yeah, but well, they're important because getting stuff incorrect is a problem. So here the question was, we have 3 threads now. Which strings can be output when running these 3 threads in parallel? So what can happen here is exactly the situation that was just described. We're just entering this while loop without waiting for any semaphore. So T1 could start printing an A, or T2 could start right away printing a B. Which one it is depends on the scheduling order. T3 cannot print because it's waiting for SC as its first instruction in the while loop. So now what happens is T1 and T2 signal SC, and then wait for a signal for a semaphore as A for T1 and SB for T2. So here in T3 we have this trick. We're actually waiting for semaphore 2 twice. So we've seen semaphores count, and here's really one of the few use cases where we use counting semaphores. So after printing an A, thread 1 increments SC. We had an initial value of 0, so here it's 1. Then maybe we print a B, we increment SC, it's a 2. So maybe we have a 2, then we switch over to T3, so it decrements to 1, it can continue, it decrements to 0. We're in the critical section here and can print a C. It could also happen in another order, so we could print an A first, signaling, then T3 could proceed until the end of line 3. Then we could switch to T2, and then when T2 has executed line 4, we could fall through to our printf in T3. So essentially, what this means is we can always have A and B in arbitrary order, but after printing an A and a B, we always get a C, and then T3 signals both of our threads T1 and T2 to continue working. So these have been waiting for these respective semaphores in lines 5 of T1 and T2. So essentially the output is what I described here in this very strange thing. And this is of course not the literal output. This is what we call a regular expression. So a regular expression is a bit of a pattern that describes regular things. We'll give a bit of a detail here. They're very useful. For example, later when you're interested in compiler design, they're very useful when you want to match text strings on the command line with tools like grep or set or something like this. So this regular expression means we have either AB as a sequence of characters or the sequence BA, depending on if T1 or T2 started first. And then we have a C, and this group is around brackets around it is repeated with a plus. So we have arbitrary many repetitions of this. So regular expressions are very useful for specifying this, because specifying this in text would have been quite, a lot of stuff to write. Okay, now the discussion starts about describing syntax for regular expressions. We should use round instead of square brackets. Now, I think in Unix, you have at least 3 or 4 different standards for writing regular expressions. This one here was done from memory. So I think Vim uses a different one from Perl, uses a different one from set. So this is a problem that there's no real standard for it. And people get, including me, get really confused. So essentially what this means, yes, you can probably put round brackets around this instead of square brackets. But in a sense, it should mean like we start either with a sequence AB or with a sequence BA, then a C, and then we repeat that all over again. But yes, regular expressions, there's a whole book on this, and I've read it. years ago as a student from start to end, and it's 450 pages. So you can spend quite a lot of time on it. And you'll learn more about this in the compilers course if you're interested, definitely. But I can also give you some links to regular expressions because they're very useful also when you use Unix day by day. Just took a note on that. Okay. More on deadlocks, and we're finally sick of this stuff, hopefully, after a bit. So we have two threads in parallel again. We have two semaphores. And the question was, executing the threads in parallel could result in a deadlock. Why? So it's again the old trick of figuring out where to switch processes. And here we first consider just this abstract model of switching between C instructions. So you could run until line 4. So we have waited for log 1 and switch over to thread 2 here. So thread 2 would then wait for log 2, increment y, and then wait for log 1. And now then switch back. So T1 would then in line 5, our red line marked in red here, wait for log 2. It has to wait because T2 already holds it. And then we switch back to T2. T2 would wait for log 1. Log 1 is already held by T1 in line 3. So here we have this mutual waiting condition, this circular link in our graph, essentially, that implies that none of our threads is able to proceed here because one would have to signal one of the logs and none of them can proceed here. So this is this mutual waiting condition we've described. This is not resolved. But of course, this deadlock does not occur in all execution or task switch orders. So it only happens, for example, in this order if we switch exactly on that in these points in time or in these places in code. So what could also happen is T1 runs to completion and then T2 runs as a very simple example. All of them would be happy and we would get results out. So, of course, one question is, are there other execution orders leading to a deadlock? Yes, you could start with T2 and then essentially just do it the other way around. And you would also end up in a related deadlock here, but this is not, these are not the only cases that can happen, as you can see. So what are the possible values of X, Y, and Z in the deadlock state? So no matter if you use the first or the second example here for a deadlock, for both cases, then you can just follow this up. X and Z are set to 2 and Y are set to 1, because these are the instructions that could be executed before the lock in line 4 on the right-hand side and line 5 in T1 on the left-hand side would actually lock up our system. Now, the other question was, what are possible values of X, Y, and Z if the program terminates successfully without a deadlock? And here I gave a hint of what we discussed before. That's such an assignment like Z equals Z plus 1 consists of multiple atomic operations on machine language level. So the simple case, first T1 runs to the end, then T2, or the other way around. We would have the value 3 in all variables here. But we could have a thread switch also occur in the middle, for example, of line 8 of T1. So in, this is nonsense. In the line 8 of T2, of course, the equals sign marked in red here. So before Z is written back, so we have actually calculated Z plus 1, but we haven't written it back. So we switch to T1, execute T1 till the end, and we switch back to T2. So we still have the old Z plus 1, which is 1 in the register, and write it back to Z. So we just overwrite the value of 2, which was written by T1 after it was scheduled. So that's one of the things that can happen here. So here we would maybe end up with Z equals 1. That's only one of the cases. And if you're interested in figuring out more, can you find other possible orders that run to completion? And what are the values? I'm not giving all the details here, so that's something for you to think about. I think the idea should be clear here. And this is one of the things students really hated the exam, I know, from experience. I guess you can still expect maybe one question about semaphores and synchronization. But of course, we'll not focus on this. I've seen operating system exams that have like half of the questions on semaphores and deadlocks, and that gets boring quite a bit. So we'll try to distribute this quite a bit over the whole contents of the course, obviously. And as you might have noticed, I also put up the exam from last year as was requested. So sorry, this is in the horrible PDF output format of Inspera, because we don't have a nice LaTeX version here. So you can check that we cover a number of topics in the exam here. So any more questions on the exercises? I'll check the backlog. Okay, more discussions about volatile. As I said, I'll send you some more information about volatile if you want to read up on this. And I think there's a comment by Hans Marius. For the exercises in TDT4186, we programmed a microcontroller which did not have an operating system, right? So that was Rakesh's course, I think, right? And in that case, we had to place data and memory addresses manually. We used the volatile keyword, but that was for a different reason. Yes, this volatile means compilers are usually optimizing nowadays. So volatile has a number of different meanings. And in this case, you would need volatile to really keep your compiler from optimizing away your write. So what a compiler does is, if it writes a value, it checks, is this value ever read afterwards? And if you write a value to like a GPIO register to turn an LED on, you're never going to read that register back. So your compiler thinks, because the compiler doesn't know about GPIO registers and hardware, so your compiler actually thinks like, oh, well, this stupid programmer has written a value which is never read back, so I can just omit that write and my code runs faster. But of course, if you omit that write, then you never write to your GPIO register and your LED doesn't turn on. That's one of the most common examples that can go wrong when you start embedded programming like this. So here you need the volatile keyword in order to keep the compiler from optimizing away this information. So this volatile then implies and tells the compiler something is happening outside of what you think your whole world of this program is. So somebody might manipulate it, somebody might need it. So that's one of the cases where you really need volatile, exactly. But there are other cases, and as I said, I'll provide some background on this on the webpage if you're interested. So we already have 2 o'clock already. So today, if you have questions on the practical exercise, Espen will be here from, he is already here, I guess, and he will be here from 2 o'clock to answer questions about practical exercises. So there were some questions if you can get support, and of course you can, because there's, well, not that many days left for us to submit. So I'll stop recording now. Thanks for joining. Thanks